Welcome to our first lesson about big idea number 3, which is compounds. So this lesson should be short and sweet and all about Lewis dot diagrams. So this should be hopefully a review from grade 11 or grade 10, but if not, that's all good too. So first of all, what is a Lewis dot diagram? Well, a Lewis dot diagram is a diagram that shows only the valence electrons in an atom or an ion. So everything that's inside a Bohr model, so the nucleus and all the interior orbitals of electrons are all kind of like replaced by just the element symbol. So in this case, we've got In here, and that's replacing the nucleus and all the lower or closer in layers of electrons, and only the electrons on that outermost shell are what we're going to draw. And the key thing to remember here with Lewis dot diagrams is that just like the Bohr model, they are pretty limited in how we draw them. So there are only ever actually going to be 8 electrons drawn at a time for any Lewis dot structure. So limitations and that aside, they are really, really useful. So let's look at how to draw them. So we start again with that element symbol representing everything in the middle, and we just want to draw those valence or outermost electrons. Remember, you can always check how many valence electrons something has for our group A atoms or columns 1, 2, 13, 14, 15, 16, 17, 18 on a periodic table by just looking at those group numbers that I just listed. It goes 1, 2, instead of 13, it's 3, 4, 5, 6, 7, 8 in terms of their number of valence electrons. Unfortunately, it doesn't work as well for transition metals, but that'll be okay because we don't use them as much for this stuff. So how do we draw them? Order matters in terms of orientation. So it's not that you need to go with the topmost position, but you do need to kind of plan it out to follow the same order in terms of going to opposite sides or same sides and spreading electrons out. So the order you want to put your electrons in goes like this. We start with 1 and 2 together. 3 goes on the opposite side. 4 and 5 fill in the empty sides, and then we fill in any spaces so that they're all paired up. That's kind of how that works. So that is our general number format in terms of filling it in. And then what that looks like when I actually want to do it is if I have chlorine, I can fill it in like this. And chlorine is in group 17 or 7A, so it has 7 valence electrons. But like I said, it's not so much that the exact orientation matters. I don't need to put 1 and 2 up here. Instead, what can happen is I can shift it around, and maybe I want that lone electron to be at the bottom. That's fine too. Or I want it to be on the right-hand side instead, and that's fine too. As long as I end up with 7, and I start with that initial 1 and 2 paired, and I start spreading them around from there, it doesn't matter. I could even hypothetically have just 1 electron up at the top if I really wanted to, but it's all relative to how you're drawing it. So why do we need to draw Lewis dot diagrams? Well, because we show bonding really well this way, because bonding occurs with only our valence electrons. So you can see in this example that chlorine with another chlorine actually will share 1 electron each and form a single bond, and it is good to go. And remember from grade 10 that we draw a line to illustrate a single bond with 2 electrons being shared. With oxygen, we can still show how it bonds. Remember, we're looking for 8 valence electrons in everything to make it happy. So we can kind of see this happening here. And so oxygen becomes double bonded. But we're showing this again with Lewis dot diagrams because bonding involves valence electrons. Lewis dot diagrams show valence electrons without having to draw all that other stuff. So we have nitrogen here as well, trying to make itself happy, and it triple bonds to do that. So that is how Lewis dot diagrams work. So that's our first lesson, and you can always fall back on drawing Lewis dot diagrams for kind of understanding how things are bonding, and even so far as figuring out how many of each of a specific substance are actually in a compound.